Hello, I'm Sara Pizzolin, coming from University of Ljubljana, and today I will give a presentation on the new design proposal for stiffened curved plates under compression. It has become widespread in the last 2 decades to employ curved panels in the construction of steel bridges. In this presentation, I will be focused specifically on longitudinally stiffened, transversally curved plates representing the bottom flange of a box girder. In this case, the curved bottom flange is longitudinally welded to vertical or inclined web plates to form a closed box section. One of the most recent bridges incorporating a curved bottom flange is the new Genova bridge in Italy, which replaced the old Morandi bridge that collapsed in August 2018. The design of curved plates is not the subject of structural Eurocodes. Actually, Eurocode 315 is limited to flat-plated structures, and Eurocode 316 refers to shells of revolution. Several studies showed that the elastic buckling stress and the resistance of curved plates are both strongly affected by curvature. Some authors already proposed approximate methods to evaluate the ultimate resistance of unstiffened curved panels. When it comes to stiffened curved plates, there is again lack of practical design rules, and the research is very limited. Most of the available research actually comes from the marine construction field, where the geometry, materials, and imperfections are not directly applicable to bridge design cases. On top of all, none of the mentioned numerical analysis has any experimental background. This is why we decided to perform experimental and numerical evaluation of stiffened curved plates and to propose new design rules. Most of the work was done in the framework of a RFCS research project Outburst. Experimental tests on 9 isolated stiffened steel plates subjected to uniaxial compression were performed in the Laboratory of Structure and Traffic Engineering at University of Ljubljana. The height of the specimens was approximately 1.8 meters and the width was 0.6 meters. The experimental setup was designed to achieve uniform compression in the panel and to avoid any eccentricity in the load application. The hydraulic piston was installed in the main test frame along with the vertically positioned test specimen, and the load was distributed uniformly on both the panel and the longitudinal stiffeners. The curved edges of the specimen were fixed and the longitudinal vertical edges were simply supported. The tests were displacement controlled up to collapse. Specimens with different parameters were included in the tests to study their effects on the ultimate resistance. 7 curved and 2 flat panels were tested. They were made of different high-strength steel grades, and all of them were stiffened with 2 longitudinal stiffeners, but some of them with 1 and some of them with 3 transverse stiffeners, and this resulted in 2 different aspect ratios of panels. The curvature of the panels is described with the curvature parameter z that is calculated as the square of the width of the panel divided by the radius of curvature and thickness of the panel. Experimental results are divided in 2 parts. On the left, there are the panels with higher thickness, and on the right, the ones for more slender panels. You can know the difference in the resistance between them, and of course the thicker panels reach a much higher resistance. On the left diagram, with the orange color denotes curved panels, and the green is for flat panels of the same dimensions. You can see the curved ones reached 15 to 20% higher resistance compared to flat panels. On the right diagram, with red, there are panels with higher aspect ratio of alpha equal 1.5, and they are compared to the dark green panel that represents the one with a smaller ratio. You can see they all yield a similar resistance. And this is a very important conclusion, which is later also confirmed with numerical results. And at last, the blue color denotes the specimen with steel grade S700 that reach much higher resistance compared to the others with S500. In general, according to the measured displacements and strains, failure was associated to a combination of buckling and yield of material for the thicker panels, and mostly to buckling for the more slender panels. In this animation, you can observe the development of the out-of-plane displacements at different loading stages. The figure on the top represents the deformed panel after unloading. So here you can see the first buckle, and then the second and the third one. So in order to assess the general behavior of stiffened curved plates under pure compression, a simple numerical model was created where the geometry was restricted to longitudinally stiffened panels between transverse stiffeners. A panel stiffened with 5 regularly spaced trapezoidal longitudinal stiffeners is considered. The external load is introduced by a uniform compressive shell edge load in the longitudinal direction, and it's acting both on the main plate and the stiffeners. The study includes a variety of geometric parameters, such as different curvatures, going from 0 to 500, 3 different sizes of stiffeners, 4 different panel thicknesses, and 7 different aspect ratios of the panel. The initial imperfections were applied as equivalent geometric imperfections with the shape of sinusoidal functions. Global and local imperfections are applied in the model, and 7 different combinations of initial imperfections are considered for each set of parameters, as shown in this figure. For each set of parameters, we performed 7 analyses, and the characteristic resistance of the plate is finally defined as the most unfavorable of the 7 resistances. The results of the numerical study show that the resistance of stiffened curved plates is less sensitive to the form of initial imperfections compared to flat panels. An example is given for a plate with curvature zeta 400, where the difference between the resistance for the most favorable and the least favorable imperfection shape is only 2.5%. While for a flat plate with the same dimensions, the difference is 19%. The results show that curvature has a large influence on the resistance of curved panels. Actually, the resistance is in general always increasing as the curvature increases. This diagram gives an example for long, highly curved panels with flexible stiffeners, where the resistance is twice as high as for flat plates with the same dimensions. These two charts give the results for plates with different aspect ratios. They show that at high curvatures, the resistance is not affected by the aspect ratio. It is because the resistance for highly curved panels is mostly governed by local buckling. This is an important conclusion because it leads us to the possible reduction of the number of cross frames by introducing curvature. Reducing cross frames means a reduction of material consumption and welding, and in a brick structure this leads us to 2 very important benefits. These are the reduction of fabrication costs and environmental impact. Here we are comparing stiffeners for different sizes. As you can see, the resistance of a stiffened curved plate is not affected by the stiffener size at high curvatures. This is because at high curvatures, the size of the longitudinal stiffener does not add much to the cross-sectional moment of inertia, since the plate itself has a much higher inertia compared to the flat plate. Smaller stiffeners affect the overall structural weight and material consumption, but more importantly, they simplify the assembly of transverse stiffeners or cross girders with the panel. Comparison of the numerical results with the design guidelines for flat-plated structures from Eurocode 315 show that the use of Eurocode neglects the positive effects of curvature and leads to extremely conservative results. This is why we developed new design rules for stiffened curved panels. The presented method is intended for practical use and is in accordance with the design rules for flat plates, but it takes in account the positive effects of curvature. So, similar to flat plates, the resistance is determined by the interaction of local buckling and of subpanels and global buckling of the entire stiffened plate. First, we calculate the local and global curvature parameters, and then the effective areas are calculated for stiffeners according to Eurocode 315, because they are composed of flat panels. And for the main panel, if local curvature of subpanels equals 1 or less, we follow Eurocode 315. Otherwise, the rules proposed by Martins should be used. The two articles with the rules are referenced at the end of the presentation. For the global buckling reduction coefficient, we calculate the shell-like buckling and then the column-like buckling coefficient, and finally interpolate them according to Eurocode 315. The shell-like and the column-like buckling coefficients were derived by the authors. For shell-type buckling behavior, the elastic critical buckling stress and the buckling coefficient were derived in the recent article by the authors that is referenced at the end of the presentation. Both equations depend on the moment of inertia of the cross-sectional area of the longitudinal stiffener and the adjacent parts of the curved plate. When having the critical stress, the reduction factor for shell-type buckling, ρ, is again obtained from the rules proposed by Martins. At last, for column-type buckling, the elastic critical stress is calculated for the entire curved cross-section in compression, and the reduction factor is determined according to Eurocode 311. Finally, these diagrams show the comparison of numerical results, the Eurocode 315 procedure, and the new design rules, which are the red lines. We can see good correlation with the results. This means that the new rules allow us to take advantage of the positive effects of curvature, especially for short panels. While for long panels, the proposed equations yield somewhat conservative results. This is mainly due to the fact that the procedure neglects the positive influence of torsional stiffness of stiffeners with a close cross-section. But this is the same conclusion that we can make also when comparing flat panels with the existing rules from Eurocode 315, because they strongly underestimate the numerical results for aspect ratios larger than 1. To finish, these are the references mentioned in the presentation, and thank you for the attention.